Okay, so we started with 4.1 and logarithmic functions yesterday. Was there anything on that material that you had issue with or had a difficult time with? Anything you would like for me to go over again? Okay. All right. Let's see who else. Shayna, did you have anything from 4.1? Welcome, by the way, that you wanted me to go over again? Okay. All right. Then, let's see. Okay. Then what I'm going to do here is I am going to do the applications from 4.1, and then we're going to start in on 4.2. So that is today's plan. We're going to begin with some of the applications of the log of exponential functions. Sorry. Hey, Shayna. You can't. Oh, no. Oh, no. Okay. Okay. What is this? All right. Hey, Ben. Set him straight, Ben. They're all online now. Everywhere we go, they're all online. All right, so Shayna is here, but she can't hear me. So I'm recommending that she restart her computer. I don't know what else to do. We could have her call in. Okay, good. All right, so you can hear now too, Shayna? Okay. Oh no, why did I just get an uh-oh? All right. Okay, if anything happens, let me know. I just had a little uh-oh come across my computer. So we'll do this for as long as we can. Okay. All right, so today we're going to do some applications from 4.1, and then I'm going to start in on 4.2, and that's the goal for this afternoon. All right, so 4.1, we did some exponential functions yesterday, and the only thing I didn't get to were to walk you through some of the examples. So there are 3 application problems. I shouldn't say examples, applications. There are 3 application problems that I wanted to talk with you about or show you how they went. The first is similar to problem number 53 in your textbook. It says that a bacteria culture contains 1,500 bacteria. In its initial count, so initially, and it doubles every hour. Part A says to find a function, n, that models the bacteria after T hours. The second part of this problem says to find the bacteria count after 24 hours. Okay, thank you. How's that doing? Are we back? Oh, it is, isn't it? Okay. So let's see. All right, how are we doing? We're back? Okay. So for part A, to find the function n that models the bacteria after 10 hours, after T hours, sorry, we're going to use a function that generally looks like n of T, where n is the number of bacteria and T is the number of hours, has to equal T of 0 times a to the x. Remember, we're in an exponential function, so we need this a to the x. What you need to know is that T is your time in hours. P sub 0 is your initial population. Or your beginning population. A, your base, is your multiple or multiplier. So what's happening every hour? So in our case, our initial population is and since it doubles every hour, this is giving us our A value. Oh, shoot. We want to do this, guys. That's my mistake. This needs to be a T, not an X. I don't need two different letters. Okay. All right. Now, for part B, this is it. This is the formula. This is our function. N of T would be 1,500 times 2 to the T. That's it. Find the bacteria count after 24 hours. They're telling us the t-value. So now we're finding n of 24, which would be 1,500 times 2 to the 24. And then all I'm doing is plugging that into my calculator. And it's going to give me some incredible number, which is 2.5165, or well, let's just do 166, times 10 to the 10th. Now, 10 to the 10th is about a billion. So this is about 25 billion. Or 10 to the 10th is about 10 billion. There we go. That'd be 10, I'd have to move it 10 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hold on, I better check that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 25 billion. That's a lot. Okay, questions about that one? Okay. All right, the second example has to do with compound interest. You may have had some compound interest in different classes. If you've ever taken a personal finance class, you may have done this already. But we're just going to do it a little bit here, and then we're going to do APY. Both of these are in the 4.1 section. And so I wanted to spend a couple of minutes on them. All right, so if $10,000 is invested at an interest rate of 3% per year, compounded semi-annually. Find the value of the investment after. Then there are 3 parts. Part A says 5 years. Part B says 10 years. And part C says 20 years. There is a formula for compounded interest. It is A is equal to P times 1 plus R over N to the NT power. And you need to know what everything stands for. A is the total amount. So that's investment plus interest. P stands for principal. That's the money investment. R is your interest rate, but we put it in decimal form, not as a percent. N is the number of compounds. And T is time in years. Okay, so for part A, we're finding the amount. Our principal is the amount of the initial investment. That's our $10,000. 1 plus our interest rate is 0.3% as a decimal. The number of compounds is the number of times in a year it's compounded. This one is semi-annually. Semi-annually is how many times a year? So our N is 2 for this problem. And we're going to take that to the N times T, or 2 times 5 power. So we're going to have 10,000. 1 plus 0.03 divided by 2, and I'm going to take that to the 10th power. And I get $11,605.41. So after 5 years, if I started with $10,000, I will now have $11,605.41. It is worth noting, that had I typed this into my calculator slightly differently, if instead of taking it to the 10th power, I had typed it in as 2 times 5, notice no parentheses, just 2 times 5, I will get an incorrect answer. Because what your calculator is doing in that case is it's squaring all of that and then multiplying that answer by 5, rather than taking it to the 10th power. It will make a difference, just an FYI. So what happens in 10 years? What would 10 years do to this problem? It seems like if you double the time, you should double your money. But unfortunately, that's not what happens. And certainly, if you do it for 20 years, it seems like you should eventually double your money. But even after 20 years, we're still not doubling our money. So you can see it will take us several years, more than we thought maybe, to get double our money in here. That particular question That particular question needs 4.3. Or if you've had some of this already, it needs you to remember your logarithms. So if you've had logs, that may be a little bit familiar to you, but don't back yourself into this corner for this assignment. You cannot backtrack and find the exponent yet, right? Okay. All right, the other one or last one here was problem number 63, and that's on APY. Or annual percent yield. Annual percent yield is the additional percent earned on investment. 1 year. So sorry, I need to reference my book because they do. Okay. In order to find your APY, you can use the 1 plus R over N to the NT power, but you have to subtract 1. So if you are asked to find the APY for an investment that earns 8% a year, compounded monthly. Your APY would be 1 plus, our rate is 8%, dividing that by the number of compounds in a year. And if we're compounding monthly, then our N would equal 12. We're going to take this times N, or to the NT power. Our N is 12. Our time is 1 year. So 1 plus 0.08 over 12 to the 12th power. And we will need to subtract 1 from it. So 1 plus 0.08 divided by 12 to the 12th power minus 1. And I get a 0.08299995, which is about an 8.3%. Right? Questions on that APY? Austin, anything from you?
No.
Shayna, still good? Okay. All right, good. Those are the only 3 examples from 4.1. So with those being done, I'm going to dip into 4.2. All right. So here we go then. So our next section is 4.2. This is our natural exponential function. Okay. How do I want to say this? All right. We already know that for an exponential function, f of x is equal to a to the x. A has to be greater than 0, and a cannot equal 1. Right? Has to be bigger than 0, except with the exception of 1. Because if we get 1, we get a horizontal line. There's no growth. 1 is just going to be a flat line. There's no growth. So the natural exponential function. Today we're going to look at, how do I? Okay, today we look at E. All right. Have y'all heard of E before? Awesome. Ben? Maybe. All right. Shana, is it ringing any bells for you? Okay. All right. So let's do a little bit of review. What is E? All right. E is a number like pi is. Okay. E is like pi because it represents the idea of a number that doesn't have an exact answer. If I ask you what pi is, like what's the value of pi? So how much is pi worth? What comes to your mind? When I say pi, you think 3.14. Good. We have an approximation for pi and one that everybody pretty much agrees on, and that's 3.14. Or for some people, they think, oh, just a little bit more than 3. But in reality, pi is a number that doesn't have an exact answer. The number itself goes on forever, 3.1415926, and the decimal places just keep going. In fact, some of you may have had a grade school teacher that had you memorize them as like extra credit or bonus points or race. I've seen elementary school teachers do it like as a race, which kid can memorize the longest decimal places of pi, right? We have uses for all of these decimal places of pi that have nothing to do with the number pi itself. I find it kind of interesting that the decimal places of pi are used to check the speed and accuracy of our computer systems. So they might send a computer out to find the millionth place decimal place of pi, and the speed with which they do it, the processing speed, tells them about the computer. So there are uses for it. But we want to talk about, sorry, tangent. We want to talk about E today and what E is defined as. So E is defined as the value of 1 plus 1 over n to the nth power as n goes to infinity. So I'm going to set up an XY table. I'm going to set up an N. And then on the other side of the table, I'm going to have 1 plus 1 over n to the nth power. And I just want us to take this pattern as far as we can for right now. Okay? So keep in mind that our n's will all be greater than 0, but our n cannot equal 0, because if our n is 0, this implodes right here. That 1 divided by 0 implodes and we can't do it. So we have to start with a number greater than 0. Just to keep it easy, I'm going to start with a 1. If I let n equal 1, then I have 1 plus 1 over 1, that's 2, to the first power. That's a 2. If I let n equal 2, then I have a 1 plus 1 half to the second power. And if I do 1 and 1 half to the second, let's clear this out, 1.5 to the second power, I get a 2.25. If I did a 5, I'm going to jump a bit. This would be a 1 and 1/5, or 1.2 to the fifth power. And I get a 2.48832. Now, just given those 3 results, what do you notice? Are the values increasing or decreasing? Right, we got a 2, we got a 2.25, we got a 2.488. If I let my n equal 10, this would be a 1.1 to the 10th power. Or 2.59374246. Gonna keep going. Now, this is not going as fast as I wanted, so I'm going to jump by a power of 10 to go to the 100. So this would be a 1.01, or a 1 and 1 over 100 to the 100th power. And I get a 2.704813829, keep on going. If I did a 1,000th power, I get a 2.716923932, and it keeps going. Are you noticing anything about this particular pattern? Yeah, I mean 2.7, it's still getting bigger. 2.71, still larger, but the gap is sort of closing, right? It's no longer getting larger by much. And if I do it to the 10,000th, I get 2.718145927. It's still larger, right? 2.716, 2.718. I'm still getting larger, but not by a whole lot anymore. 1.12341. And you see there starts to be some repetition, right? So it's almost as if there's an asymptote here. Do you know how when we do exponential functions and it approaches but never touches zero? This is approaching but never really ending up to be a number either. Right? Each iteration, each attempt gets us closer and closer to a number, but we can't pin it down exactly. We can, however, say that it would be true that E is approximately. There you go. We usually give E to 3 decimal places, and we usually say a 2.718. It's an approximation. In the same way that when you get pi and think 3.14, we now need you to see an E and think 2.718. Or if you'd rather, just like pi is a little bit more than 3, E is a little bit less than 3. Questions? Okay, that gets you some clarity on E and what it is. Now, the first thing your text is going to have you do with it is to well, okay, I shouldn't say that. Let me backtrack just a minute. The natural exponential function then is f of x is equal to e to the x. With base e, this is often called the exponential function. So I only mean this because sometimes you will see this in reference. So sometimes they'll say using the exponential function. And when they say using the exponential function, they're talking specifically about f of x is equal to e to the x. It is one of those stupid little hang-ups that we math people do sometimes. It's clear, but it's not clear. It's like secret code, and if you're in the know, you know that the exponential function is e to the x. Right? We can use this to find values. For example, what is e to the fifth? Or e to the 0? Or e to the negative 1? Now, I don't want you to think this is particularly difficult. It's really not. You just need to know your calculator. Every calculator has an e to the x button on it. Let me zoom in on this guy. Focus, focus. So on my calculator, you can see it's in the first row there, and it says e to the x. So if I have to find e to the fifth power, I'm going to shift so I get an e to the, and you see it opens up the exponent. I'm going to type in a 5, and it's going to give me what e to the fifth is, and this is approximately 148.413. I'm giving 3 decimal places. E to the 0 works just like any other exponent. So anything to the 0 power is always 1. Don't overthink it. E to the negative 1 can be done the same way. To get a 0.368. And you can really find e to any power just using it as a regular power button. So here I have e to the negative square root of 2. So I'm going to do negative square root of 2. And that's going to give me about a 0.243. If I have to have 4e to the third, that's just a order of operation, 4e to the third, 80.342. And e to the 5.7 would be done just as any other power. So I got 298.867. All right, any questions? Okay. All right, so that's only the That's only the first part of 4.2, but that's really all I wanted to work on today, was to just do those applications and then get a definition and some use in or some playing in with the value of E. So I don't have anything else that has to get done today. If you guys have other usage of your time. Yeah? Okay. All right. Thank you all very much. Stay safe, stay sane, and we'll see you tomorrow. All right. Bye-bye, guys.